Okay. The next thing is what we started last time towards the end of the class. Now we are moving towards getting sort of control of everything. One thing is about the possible conjugacy classes in Sn. And as you know, Sn is the big daddy group. You know, if you know everything about Sn, then you know a lot about all the subgroups as well. Yeah. Okay, so you didn't see these transparencies. This is what I meant. This was shown, I think, right? This you saw, and then this was just actually what we did in the first half of the first 10 minutes of the class, 10-15 minutes, and we had the theorem about equality of lengths of cycles for regular cycles forming order n subgroup of Sn. Okay, now comes this statement we were trying to make last time. So we want to study the conjugacy classes of Sn written as cycles. Generically, we will have something like this A1, A2, AK, B1, B2, BK. So suppose there is a cycle of length k, and suppose it occurs several times. There is one cycle of length k, then another cycle of length k. They are occurring several times. Suppose this number is nu subscript k. This is all going to get a little confusing, but not later. Once you read it again, it will not be so bad. So consider nu k, which is the number of cycles, all of length k. Okay, this we note as the notation for it is k to the power nu k. And that is in a sense the total number there as well, because it's product of k nu k times. So it is k to the power nu k. Now suppose you have a cycle like this in S9. Suppose consider permutation group S9. In it you have this particular cycle. Let us check that every element occurs in it. 1, 3 occurs, 5, 4 occurs, 2. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. But there is a 2 cycle, there is a 2 cycle, then there is a 3 cycle, then there is 1 cycle and 1 cycle. Actually this is not how the educated books will write. They will probably order it by putting 3 cycle first, then 2 cycles and so on, but this is how I have written it. So if you do it, then in this notation that was suggested here, what it means is I have 2 cycle, 2 of them. So k is 2 and there is 2 of them. Then here k is 3. The cycle size is 3, but there is only 1 of it. And then there are 2 1 cycles. So 1 to the power 2. So the cycle structure of this is written out, actually it should be written 3 times 2 to the 2 times 1 to the 2. And sometimes the 1 cycles are not written. Okay, that is when you know from context that the carrier space is already size 9, and if you then see 2 to the power 2, 3 and stops there, then you guess that yes, there are 2 cycles of size 1 which are not written. But so this is one notation for writing out cycle structures in compact form. So that is when it doesn't matter what numbers and what details these are. Ultimately it only matters how many cycles of a given length there are in a particular element in pi n, in Sn. Now we note the following. If I take 1 times nu1 are all cycles of size 1. I multiply it by 1. So that counts all the elements that have fallen in cycles of size 1. Then I take 2 times nu2. Nu2 is the total number of cycles of size 2. I multiply it by 2. I get all the elements of the carrier space that went into 2 cycles. If I do this sum up to k times nu k, I should recover all my balls in the carrier space, all the n elements of the carrier space. So this summation equals n, the total number of elements in the carrier space. Here you can see 2 times 2 plus 3, so 4 plus 3 plus 2 is going to give back 9. Okay. So this is a fact. Now the way it is written, it doesn't look very powerful. But so clever people of course sat around and said, instead introduce lambda subscript r. So trade nu with lambda. So here I should have added something in the notes, but I'll add it later. But let me switch here. And sometimes this is called length of the cycle, of length k in a length k. Okay. Thus a particular element in Sn can be represented. This does not represent the thus the class of a particular, okay, the conjugacy class, okay, can be represented through its conjugacy class as k to the power nu k into k minus 1 to the power nu k minus 1, etc., and times 1 to the power nu 1, which is sometimes omitted. Alternatively, so one statement that I don't know whether I have written earlier in the notes and didn't say it, but so the size of the this particular, let me write over here. This structure does not change under conjugacy transformations. i.e., if B equal to sigma A sigma inverse, then A and B have same cycle structure. Okay. And this is called its conjugacy class. So that is why it is interesting to focus on this, because this way of writing out the designation of the class is not going to change under conjugacy transformation, conjugate transformation. So conjugacy class remains the same under under conjugacy transformation. Next, we instead of nu k, we change notations to by defining lambda k to be equal to sum from r equal to k, this whatever k here is, up to n of nu k. Now this may look a little silly, why are we doing this? This is, so what happens as a result of this is that lambda 1 then is equal to nu 1 plus nu 2 plus up to nu n, right. Then lambda 2, that from this instruction starts with r equal to 2 and goes upward. So it is equal to nu 2 plus up to nu n, and so on, so that if I add all these, then here I get lambda 1 plus lambda 2 lambda n. So, last entry will be nu n equal to lambda n, right, because if you ask for what is lambda n, the summation has to start with n and end with n. So, it just gives nu n. So, this set of equations sums to giving sum of lambdas on this side, but on this side it exactly produces k times nu k. Right, because you can visually see it has nu 1 once, it has nu 2 twice, it will have nu r times, and it will have nu n times. So, it exactly produces k times nu k summation, but this summation we saw is equal to n. Therefore, coming back to the lambda 1 plus lambda 2 lambda n equal to n. Okay. Now, you will say what is the great achievement, but one thing that has to be pointed out is that the transformation is reversible. The lambdas are defined in terms of nu. You can always recover the nu's out of the lambdas because this set of equations is linear, and you can extract any particular nu r by just subtracting two successive lambdas. So, if I subtract lambda 2 from lambda 1, I get lambda 1 out. So, also note the inverse transformation. Also linear, which is simply that nu k is equal to lambda k minus lambda k plus 1, because k plus 1 is going to start with nu k plus 1, whereas lambda k would have started with nu k and then also have k plus 1 and all the others. So, if you subtract, you recover nu k. So, it is a unique mapping back and forth without any loss of information. So, coming back to this, so we can now write this as lambda 1 plus lambda 2 lambda n. So, as I was saying, why would you change from one set of symbols to another? After all, it's a one-to-one mapping back and forth. But the point is, now we can read this off as Ramanujan would read and say these are partitions of n. Okay. Given an integer, these are its partitions. Therefore, the number of possible cycle structures you can create in Sn is equal to the number of ways of partitioning n. In number theory, there is, or now you learned number theory here. Given a number n, what are all the ways of partitioning it into smaller integers? This is called number of partitions. So, let us see an example. So, start with 1. If n is equal to 1, then there is only one partition. You can write it as 1. If n is equal to 2, then 2 can be written as equal to 2 or can be written as 1 plus 1. So, there are number of partitions is 1 here, here it is 2. Now, you have to count how many of these are. N equal to 3, 3 equal to, we can write of course 3 itself, then we can write 2 plus 1, and then we can write 1 plus 1 plus 1. So, there are 3 ways of partitioning 3. When we get to n equal to 4, 4 is equal to 4. So, remember that in our, I do not want to confuse right now, but you can always write it out in terms of saying this is 1 to the power 3, this is 2 to the power 1, 1 to the power 1. So, can also be written as you would have written in cycle notation. So, 4 is 3 plus 1 is equal to 2 plus 2, or is equal to 2 plus 1 plus 1, or is equal to 1 plus 1 plus 1 plus 1. So, here we got 5 partitions. The point is, this enumeration cannot be generalized. There is no formula, which is why Ramanujan went at it with full force. So he guessed all kinds of things about where the partitions were easy to calculate, and finally Hardy and Ramanujan proved a very difficult theorem which gave an asymptotic formula. In the limit of large n, what are the number of partitions you can have? There is a Hardy-Ramanujan formula. But right now, just to get over boredom, you can partition 6 in your notebook. What are the partitions of 6? So what answer did you get? 11 partitions. Very good. Okay. So I passed. So we get 11 partitions. So this formula, and now you have control about over Sn, because you have all the possible cycle structures that can possibly occur in Sn. Okay. And if we go to our 6th example, then you can see that all the groups of size 6 that will get embedded in S6 will necessarily have 6 cycle structure. Remember that they have to have n things listed, and they are regular cycles. So they have to have size 6. They may be split up as so they can have size 6, or they can have 3, 3. So we can highlight things that are regular here. So 6 qualifies, 3, 3 qualifies, because remember they have to have cycles of equal size, and 2, 2, 2 qualifies, and then 1 is of course identity element where nothing shifts. Yes. Lambda values and not new values. You are right. So this is not the correct. You are. Thank you. So that's right. So this is not. This doesn't list the regular cycles here. Quite right. Okay. But the point is, you can work backwards to see how many of these partitions will qualify, not these partitions, but after recovering news from them, which are the partitions which are acceptable as regular cycles, because they will be necessarily of equal size. And the subgroups that you form will only be formed out of those. The n size groups will only be those. So you have a lot of control over this. And of course, any things that, what the other thing I wanted to say from this was, all those things that there were plus ones are essentially members of Sn minus 1, lower size Sn groups. For example, this 111 is essentially an S3 member. So only 3 cycles are important, other 3 elements are not being touched. Again, I am sorry, I have to say, only in the new picture. If it was the new picture, then that would be correct. So lot of them will essentially be reproduction of smaller permutation groups, and then the essential ones will come at where all the elements occur, the regular cycles occur. Okay. So the theorem, as we said, is the number of possible cycle structures in Sn is equal to the number of ways of partitioning n. Now there is a concept of order of a conjugacy class. So you might ask, given a particular partition, let's say this is the particular cycle structure I have, which is actually abstractly written like this because the details don't matter. How many of such elements there are? How many elements in Sn have cycle structure 2 to the 2, 3, 1 to the 2? So that is called order of the conjugacy. So all of those will be in the same conjugacy class because they'll have exactly same cycle structure, and the number of elements in the conjugacy class is called order of the conjugacy class. So I will now write a formula, but not really prove everything, but 2 things. One, instead of writing this and instead of writing the summation that we wrote, There is another way of representing the possible cycle structures. So that is what the last line here says. Another way of capturing possible partitions is a box structure. So suppose I have S20. Okay, this 20 is chosen so that it can draw large enough a figure. What you do is take 20 boxes, there are 20 boxes here, and arrange them in various possible orders, but starting with one over here, smallest on this side and growing larger to the left. This particular pattern that has been drawn reads as follows: nu 1, the number of cycles of size 1 is 1. Nu 2, the number of cycles of size 2 are none, here 0. Nu 3 is equal to 1, so I can write 3 vertically like this. Nu 4 again is 1. There are no cycles of size 5, but then there are finally 2 cycles of size 6. So the thing that would have been written as 6 to the 2, 4 to the 1, 3 to the 1 can be also written out as a set of boxes. Now what is the advantage of writing like these boxes is that actually by assigning numbers to them according to some rules, which I don't want to enter right now, these are called Young tableaus, but you can then calculate the order of a cycle, the order of a conjugacy class, how many elements of this type can occur in a conjugacy class. This can be shown to be found from this, but you can also manually count what is the order of a class. So a prescription for counting can be used to remember, but I can tell you directly what the order of the class is, and you will, I think, believe me. Well, what is the order of the class? First of all, there are n elements, and therefore there are n factorial ways of arranging them. But when they are broken up into cycles of size length k and nu k of each type, essentially in each of them you can permute the k elements that are in a k cycle, and that doesn't change the cycle. So you divide out by nu 1 factorial, nu 2 factorial, nu k factorial, because within us things within a cycle don't matter. So those are repetitions, so we factor that out. And finally we also factor out by k to the power nu k, because that is the number of, so you have nu k boxes of size k, those also could be written in any order, it should not matter. So k to the power nu k also. So if you take n factorial and divide out by these factors, then you get the number of independent elements you will have in this particular class. So that is called order of the class. Alright. So now I come to the more exciting part, which is that with all this knowledge, armed with all this knowledge, mathematicians got very excited and they said, can we find out all the possible groups there can be, because Sn gives you so much control. So it is called classification. To go towards classification, one first defines what is called a simple group. Okay. So a group is called simple if it has no normal or invariant subgroup. Now you remember invariant subgroup is of this type. So recall a normal or invariant subgroup is, I should have written capital N, is such that if you do conjugacy transformations on it, you keep getting back N itself. So, right, so this is the definition of, so you can have a subgroup, but typically if you carry out a conjugacy transformation on it, you may get some other copy of the, and which may not even be a subgroup, you will just get another set of same size in the large group G. But if it happens that for all G belonging to the group G, any one member of the normal subgroup is transformed into itself, then that is called a normal subgroup. Now one can see the following thing. If a normal subgroup exists like this, then we can construct a factor group. You can then construct a group to be G divided into equivalence classes of n. So, well, here I am really jumping through a few things. I should have spent more time, but I want to get on to something that, so we will come back and prove this theorem. Okay. If you have a normal subgroup, then you can create a factor group such that G slash n itself has a structure of a group. The equivalence classes of G under n, the copies of n in G, they will be all, so for that one has to define the inverse relation, that is transformations of G elements under the operation of n. Then one can define, so if G1 n is n1 is equal to n2 G2, then G1 and G2 are related, sorry, G1 n is equal to n G2, then G1 and G2 are supposed to be in same conjugacy class. We are right over here. Right. In this case, we can show that the left cosets, and remember the cosets are constructed from subgroups. By left coset is G times H, right cosets are H times G. Show left cosets and right cosets n times G are identical. Right, you remember that if you had a subgroup H, if you hit it on the left with all the group elements, then the subgroup gets mapped into other copies, and these are called left cosets of it. It establishes a equivalence relation. You have to say G2 inverse G1 belongs to n, then etc. In the case when n is a normal subgroup, it will turn out that the left and right cosets are identical. And then we can construct this set of equivalence classes G slash H. So here it's actually the usual slash, but here it has a different meaning. It's the group theoretic or set theoretic slash, which says all the set of all elements in G which are equivalent up to equivalence relation defined by H. So this is called factor group. Well, first of all, it's called coset space. When H is n, G slash n equal to F is also endowed with a group structure. So this we will prove next time. If there is a normal subgroup, then essentially we can form these factor groups, but therefore if you define a simple group is one that has no normal subgroup, then that is a new unique kind of group. Okay. So thus if we classify all the simple groups, then we have full classification, because the non-simple ones will only have additional factor group structure which is already contained in some previous simple group. Okay. So the problem of understanding all the groups boils down to understanding only the ones that are simple, that don't have a normal subgroup. If they have, then anyway you have a description for that. So what are all the groups there can be? Turns out that here I have written some general thing. So possibilities for normal group are, first of all, you can think of the obvious possibility. If I have just cyclic group but of prime order, then such a group never has a subgroup, because if it is a prime order group and it is cyclic, so it's a commutative group, it's just pth root of unity where p is a prime. Such a group has no subgroup because it has no factors, so you can't make any smaller group out of it. So clearly the list is endless, that much we have proved already. The list of possible finite groups, discrete groups, is endless because primes are endless. Everyone knows primes are endless? You know, proof of Euclid? The proof is due to Euclid, that the prime, because all you do is multiply all the previous primes and add 1 to it. You obviously can't divide by any of the previous primes, so it's a new prime. So you can always construct a bigger prime given any number of primes. This is a simple proof is due to Euclid. So if you have a pth root of unity, those elements obviously form a new group. So the list is certainly endless, and the complete classification is like this. Every finite group is isomorphic to one of the following. So this is actually cut and pasted from Wikipedia. You can read Wikipedia, which is good enough for most of these things. The member of one of the 3 infinite classes of such, namely either cyclic groups of prime order or alternating groups of degree at least 5. So these are the AN groups. That is another category, and this at least 5 is interesting because this is what Galois managed to actually prove. That is why polynomials of degree 5 and higher do not have explicit closed form solutions. So the fact that 5 and higher he proved that that is what enters into trying to get solutions in the complex plane. Okay, and then there is something called group of Lie type. There is some list. Finally, what remained was some 26 kind of groups called sporadic groups, and there is something called Tith's group, which was something very unusual. You can consider it 27 unusual groups. So these are a set of groups which are sort of long list, infinite lists, but then there is a set of bunch of unusual things that are called sporadic groups. That makes up everything, and the biggest group is called the monster group. So the largest sporadic group of simple type is called Tarski monster group. The area of modern algebra, monster group M, is the largest sporadic group, having it, the order of the group is, okay, this is the order of the group, which is approximated as 10 raised to 53. But they proved that this is the largest possible sporadic group you can have. There is nothing more. This exploration was done by using a computer. Okay. So in the 90s, mid 90s, and if you read this article in Wikipedia, it's worth reading because it says that it took almost 200 years of continuously working, not 200, but whatever. Can't be because Galois is 18 something, right? So, but 100 plus years of this guess that it should be possible to classify, and the program to prove started, and various people proved various pieces of the thing. In the end, in 90s, with arrival of fast computers, some smart guys said the remaining thing we can figure out by writing an algorithm, and then they cracked it and showed that there is no bigger size simple group left. This shocked many mathematicians because they thought that mathematics was pure thought, and if a machine could find it, then it kind of was an insult to them, but they have learned to live with it now. So finite simple groups have been completely classified. Each such group belongs to one of the 18 countable infinite families, one of the 26 sporadic groups that do not follow such a systematic pattern. The monster group contains all but 6 of the sporadic groups as subquotients. Robert Grease has called these 6 exceptions pariahs and refers to the other 20 as happy family. Okay. So this is the status of group theory at present. It is quite good to see that this exists. We are at the end of the class, but I will leave you with what we will do next time. We are not interested in the mathematician's classification, but we are interested in the geometric or physical classification. And from the point of view of physics, there are again 3 broad classes of groups. There are molecular groups which chemists use, where there is essentially a standalone thing. So these are called point groups, these 2 classes of groups. There is a shape molecule of some kind, or there are lattice groups which are space filling unit cells, with each unit cell having a specified layout. That layout will be similar to molecular group, but then there is a repetition as well. There are shift operators as well. And then there are groups of regular polyhedra, but this exhausts pretty much what we would be interested in from physics point of view. And there is a nomenclature that lists all of them. We will only do the ones that chemistry, the first type, molecular groups and its classification. The others become too involved, nomenclature becomes involved, and proving its utility. So the utility of the lattice groups is essentially in X-ray spectroscopy, which most of the EP students will learn. I mean, both EP and MSc students will probably learn. So we will not actually go in, and their group theory per se doesn't play that much role. It's the geometric structure. But for molecular groups, we will see that there is some interesting result from group theory that applies to it.